What if everything we think we know about reality is just the surface layer of something far more immense and mysterious? Picture our universe not as a singular, all-encompassing expanse, but as one single bubble floating in a cosmic sea of countless others, each with its own laws of physics, its own history, and maybe even its own versions of you and me. This isn't science fiction. It's one of the most mind-expanding ideas that modern physics and philosophy have brought to the table. And today, we're setting off on a journey to explore not just one or two, but 30 astonishing theories about hidden universes, realms that could exist parallel to our own, layered within dimensions we can't perceive, or vibrating just beyond the reach of our senses. From the scientific to the speculative, each of these ideas challenges our understanding of existence in profound and sometimes unsettling ways. Think about it. What if black holes are not endpoints but gateways? What if time itself branches into infinite possibilities with every decision we make? Or what if our entire cosmos is just a simulation running in some higher dimensional computer? These are the kinds of questions that have captivated brilliant minds across centuries, and they invite us to look beyond the familiar and imagine realities stranger and more wonderful than we ever thought possible. This exploration is about more than just theories. It's about rediscovering that sense of wonder you felt as a child staring up at the stars. It's about tapping into that innate human curiosity that drives us to ask what's out there. And what if? So whether you're a seasoned science enthusiast or someone who's just beginning to ponder the bigger picture, you're in the right place. Settle in, open your mind, and get ready to venture into the extraordinary, because by the end of this journey, you may never see the universe or yourself quite the same way again. The first and perhaps most famous of these ideas is the multiverse theory. This isn't just one single idea, but rather a whole family of concepts that all point toward the same stunning conclusion, that our universe is not alone. According to this view, what we can see, all the stars, galaxies, and vast cosmic voids, is just one tiny region of a much grander, perhaps infinite reality. Think of it like this: if the entirety of existence were an endless ocean, our universe would be a single bubble rising to the surface. Countless other bubbles, each a complete universe with its own unique properties, could be floating all around us, completely separate and unreachable. This idea finds strong support from two major pillars of modern physics. The first is cosmic inflation theory, which describes how the very early universe expanded at a mind-boggling speed. Some versions of this theory suggest that this inflationary process didn't just happen once to create our universe. Instead, it might be an eternal and ongoing event, constantly spawning new pocket universes in a vast, ever-growing cosmic foam. Each of these new universes pinches off from the inflationary field, forming its own distinct bubble with its own randomly determined laws of physics. In this scenario, the fundamental constants of nature, like the strength of gravity or the mass of an electron, are not universal laws at all. They are more like local bylaws set by the random chance of how each bubble universe formed. We just happen to live in one where the numbers are perfectly arranged to allow for galaxies, planets, and life. An infinite number of other universes might exist where those constants are different, rendering them barren, chaotic, or perhaps filled with forms of existence we cannot even conceive. The second pillar comes from the strange world of quantum mechanics. The classic many worlds interpretation proposes that every time a quantum event occurs with multiple possible outcomes, the universe doesn't choose one. Instead, it splits into multiple branches, each one representing a different outcome. In this view, every possible alternative history and future is real, playing out in its own parallel world. A version of you exists who made every different choice you ever considered, living out those consequences in a reality that diverged from ours at that single moment. While this interpretation is philosophically debated, it offers a compelling and mathematically consistent vision of a multiverse where everything that can happen does happen somewhere. So why does this matter? The multiverse concept provides a potential answer to one of the deepest mysteries in science. Why does our universe seem so perfectly fine-tuned for life? If the strength of the nuclear force were even slightly weaker, stars would never have ignited. If the cosmological constant were a fraction larger, the universe would have ripped itself apart before any atoms could form. From our perspective, it looks like a miraculous coincidence, but in a multiverse, there's no miracle. With an infinite number of universes exhibiting every possible combination of physical laws, it's no surprise that we find ourselves in one of the rare habitable ones. We are simply the winners of the ultimate cosmic lottery. But if the multiverse offers a grand, almost philosophical framework for other realities, our next theory provides a potential mechanism, one rooted in the mathematics of the most ambitious attempt to unify all of physics. Welcome to the bizarre and beautiful world of string theory. At its heart, string theory proposes a radical rewrite of reality's ingredients. Instead of point-like particles, the fundamental building blocks of the universe are unimaginably tiny, vibrating loops of energy strings. And just like a violin string can vibrate at different frequencies to produce unique musical notes, these cosmic strings vibrate in distinct patterns to create every particle we know, from electrons to photons to quarks. This elegant idea, however, comes with a catch. The equations of string theory only work consistently in a universe with more than the 3 spatial dimensions and one time dimension we experience every day. In fact, they require 10 or even 11 dimensions. So where are these extra dimensions? The theory suggests they are compactified or curled up into shapes so incredibly small that they are completely hidden from our view. The specific way these dimensions are folded and twisted determines the laws of physics within that universe. It sets the values of fundamental constants, dictates how forces like gravity and electromagnetism behave, and ultimately decides whether stars can form or chemistry can happen. And this is where the concept of the landscape truly unfolds. Physicists discovered that there isn't just one unique way to compactify these extra dimensions. There are a staggering number of possibilities, a number so vast it defies human comprehension. Estimates suggest there could be around 10 to the power of 500 different stable configurations. That's a 1 followed by 500 zeros. To call this number astronomical would be a gross understatement. The number of atoms in our entire observable universe is a paltry 10 to the power of 80 by comparison. Each of these configurations represents a different possible universe with its own unique set of physical laws. Our cosmos, with its specific gravitational constant and electron charge, would be just one single, lonely entry in this impossibly vast catalogue of cosmic potential. This is the string theory landscape, a mathematical terrain of possible universes so immense that it makes the bubble multiverse seem almost cozy. It transforms the question of why is our universe the way it is? From a profound mystery into a simple question of probability. With so many options on the table, it becomes almost inevitable that a universe like ours, capable of supporting conscious life to ponder its own existence, would eventually appear somewhere in the landscape. We are not a planned outcome, we are simply one possible arrangement that worked. But how does this abstract mathematical landscape of possibilities actually connect to a physical reality brimming with separate universes? The bridge between the two is perhaps one of the most dynamic and compelling concepts in all of cosmology, the theory of eternal inflation and the resulting bubble universes. This idea takes the grand, almost static picture of the string theory landscape and sets it into breathtaking motion, describing a mechanism that could actively be generating new realities even as you hear these words. To understand this, we need to rewind to the very first moments after the Big Bang. The prevailing theory of cosmic inflation proposes that our universe underwent an inconceivably rapid exponential expansion, doubling in size again and again in a fraction of a second. This process smoothed out the cosmos, explaining why the universe appears so remarkably uniform in all directions. But what if this inflationary period never truly ended everywhere? This is the core of eternal inflation. The thinking goes that the energy field that drives this expansion, often called the inflaton field, doesn't just vanish. Instead, it behaves much like water in a pot that's been superheated. Most of the water is in a violent, boiling state, but here and there, bubbles of stable water vapor begin to form. In this cosmic analogy, the seething, high-energy, boiling state is the inflating multiverse, often called the false vacuum. It's a state of hyper-expansion, stretching space itself at a speed far greater than that of light. But within this chaotic, energetic background, random quantum fluctuations can cause tiny pockets of this field to suddenly lose energy, cooling down into a stable state. This stable state is what we call the true vacuum, and the moment this happens, that tiny pocket stops inflating at the frantic multiverse rate and begins its own, much slower expansion, effectively pinching off to become its own separate bubble universe. Our entire observable cosmos, with all its hundreds of billions of galaxies, is likely the interior of just one such bubble that formed eons ago. Now, here's where the magic and the true diversity of the multiverse comes in. According to string theory, that stable state or true vacuum that a bubble settles into isn't the same for everyone. Remember the landscape of 10 to the 500 possibilities. The specific way the extra dimensions are curled up determines the vacuum energy of that stable state. So when a bubble forms and its inflaton field drops to a specific energy level, it's essentially selecting one particular point on that vast landscape. This single event randomly locks in all the fundamental laws of physics for that entire universe. The strength of its forces, the masses of its particles, and the number of its dimensions are all set in stone from that moment forward. This means each bubble universe could be radically different from our own. One bubble might have a much stronger gravitational constant, causing it to collapse back into a black hole almost instantly after it forms. Another might have a weaker nuclear force, preventing atoms from ever bonding together, making chemistry and life impossible. And yet another might have 5 macroscopic dimensions, allowing for complexities of geometry and physics that we cannot even begin to visualize. We don't perceive these other bubbles because the walls of our own universe bubble are expanding at nearly the speed of light, and the inflationary space between us and other bubbles is stretching even faster, making them forever beyond our observational horizon. We are left with a truly humbling image of reality, an eternally inflating multiverse, a chaotic, frothing sea of space-time where new bubble universes are constantly nucleating, each one a self-contained cosmos with its own unique destiny. Some are stillborn, collapsing instantly. Others are barren, expanding forever into cold, empty darkness. And a very, very select few, through sheer random chance, get the recipe just right to birth galaxies, stars, planets, and life. We are not just inhabitants of a universe, we are residents of a single bubble in a cosmic foam, surrounded by an infinity of other realities, most of which would be utterly unrecognizable and uninhabitable to us. But if the bubble multiverse and the string landscape paint a picture of vast, disconnected cosmic domains, our next theory brings the infinite much closer to home. It suggests that with every choice you make, every chance occurrence, and even every random quantum event, the universe you know splits in two, creating a new, parallel reality where a different version of events unfolds. This is the many worlds interpretation of quantum mechanics, a concept so radical that it transforms the entire cosmos into an endlessly branching tree of possibility, with a version of you existing on every single limb. To grasp this, we first have to confront the central weirdness of the quantum world. At the subatomic level, particles don't exist in a single, definite state. Instead, they are described by a wave function, a mathematical expression that encapsulates all the possible properties a particle could have, like a blurry cloud of potential. An electron isn't definitely here or there. It has a probability of being in many different places at once. This strange state of affairs is called superposition. The classic thought experiment is Schrödinger's cat, a cat in a box that is simultaneously alive and dead until someone opens the box and looks inside. The act of observation, according to traditional interpretations, forces the particle to choose a single state, collapsing the wave function from many possibilities into one concrete reality. In the 1950s, a brilliant young physicist named Hugh Everett asked a simple but profound question. What if that wave function never actually collapses? What if every single possible outcome encoded within it actually happens? His many worlds interpretation proposes that instead of one outcome being selected, the entire universe literally splits into multiple branches. At every moment, for every quantum event, reality diverges. In one branch, you see the electron on the left. In the newly created branch, an alternate version of you sees it on the right. Both outcomes are equally real. They just happen in different, now separate worlds that proceed independently of each other. This isn't just about electrons. This process applies to every quantum event, and since everything in the universe is made of quantum particles, the implications are staggering. Every time you flip a coin, the universe splits. In one world, it comes up heads. In another, it lands on tails. In a world where you turned left on your way to work, you arrived on time. In the branch where you turned right, you got stuck in traffic and were late. A version of you exists who pursued a different career, married a different person, or decided to have that second cup of coffee this morning. Every possible history and future is not just a thought experiment. According to this interpretation, they are all physically real, playing out in their own parallel timelines. The beauty of this idea is its elegant solution to the problem of observation. There is no mysterious collapse of the wave function requiring a conscious observer. The mathematics simply describes a reality that is constantly dividing. Every version of you in every branch believes their outcome is the only one that happened because from their perspective it is. We are never aware of the split. We only experience a single, linear timeline. We are like a driver who only ever takes one exit on a highway that constantly forks, completely unaware of the other roads and the other drivers heading toward different destinations. This leads to some truly mind-bending consequences. It means that for every historical event, there are branches where things turned out differently. There are worlds where dinosaurs never went extinct, where certain empires never fell, or where pivotal inventions happened centuries earlier or later. It also suggests that unlikely events are not just possible but guaranteed to occur somewhere in the multiverse. In a world with an infinite number of branches, a deck of cards shuffled into perfect order isn't a miracle. It's a statistical certainty in some reality. The many worlds interpretation offers a universe of absolute determinism. The wave function evolves according to strict rules, but from our limited, single-branch perspective, it creates the perfect illusion of randomness and free will. Now, if the concept of branching worlds and bubble universes stretches the limits of your imagination, our next theory asks you to envision our entire reality as something even more peculiar. A single slice of a much larger cosmic loaf of bread. This is the realm of brain cosmology, an idea that emerges from the deeper extensions of string theory and completely redefines what our universe might actually be. In this view, the three spatial dimensions we move through everyday length, width, and height are not all there is. They are just the confines of a membrane, or brain for short, a vast dynamic surface floating within a higher dimensional space. Think of our universe not as a solitary bubble, but as an immense three-dimensional sheet adrift in a bulk, a space that has more dimensions than we can perceive. This bulk could be home to other brains, other universes just like ours, each one a separate sheet existing in parallel. They could be mere millimeters away from us in these higher dimensions, yet completely invisible and unreachable because all the matter and forces we know of, with one crucial exception, are stuck to our brain. It's like being a character drawn on a single page of a massive book. You're aware of your own two-dimensional world on the paper, but you have no way of interacting with the characters living on the pages above or below you, even though they are incredibly close in the book's third dimension. This leads to one of the most elegant and powerful explanations for the most mysterious force in the cosmos, gravity. Why is gravity so unimaginably weaker than the other fundamental forces? A magnet can easily lift a paperclip, defying the gravitational pull of the entire Earth. Brain cosmology offers a stunning answer. Perhaps gravity is not weak at all. Maybe it's just diluted. The idea is that while particles of light and matter are confined to our three-dimensional brain, the graviton, the hypothetical particle that carries the gravitational force, is unique. It can leak off our brain and propagate through the full higher dimensional bulk. From our perspective, this leakage makes gravity appear faint, as if its strength is spread out across dimensions we cannot access. This simple yet profound idea provides a natural solution to a puzzle that has perplexed physicists for decades. But the truly explosive implication of this model is what it suggests about the origin of everything. What if the Big Bang wasn't a one-time, mysterious beginning from a singularity, but merely the latest event in an endless cosmic cycle? This is the brilliant proposal of the Holographic Universe model, which comes directly from brain cosmology. Imagine two parallel brains, like two enormous flat sheets, drifting silently through the bulk. They could be drawn together by the gentle force of gravity acting across the higher dimensions. As they approach each other, their interaction would release a colossal amount of energy, heating the surfaces of both brains to an incredible temperature. From our perspective, trapped on one of these brains, this event would look like a sudden, hot, and ultra-dense beginning, a Big Bang. After this fiery collision, the brains would bounce apart, each now expanding and cooling, allowing galaxies and stars to form within them. A universe is born. Over trillions of years, the expansion would slow, and the energy within each brain would dilute. Eventually, the subtle gravitational attraction would pull them back together again, leading to another collision and another Big Bang, resetting the cycle. In this breathtaking vision, the universe has no true beginning and no final end. It is part of an eternal, rhythmic dance of creation and destruction, where each new universe is born from the ashes of the previous collision. Our entire cosmic history, from the first flash of light to the formation of our solar system, might just be one act in an infinite cosmic play that has been running forever. While these ideas of eternal cycles and cosmic collisions reshape our understanding of time and creation, another theory proposes something even more fundamental, that the very fabric of our reality might be an illusion. The holographic principle is perhaps one of the most profound and counterintuitive concepts to emerge from the intersection of gravity and quantum mechanics. It boldly suggests that our rich, three-dimensional existence, everything you can see, touch, and feel, might actually be a projection of information encoded on a distant, two-dimensional surface. In essence, our reality could be a cosmic hologram. The roots of this astonishing idea lie in the physics of black holes. In the 1970s, physicist Jacob Bekenstein made a startling discovery. He realized that a black hole's entropy, which is a measure of its information content or disorder, is not proportional to its volume as you might expect for a three-dimensional object. Instead, it is directly proportional to the surface area of its event horizon, the point of no return. This was a huge clue that the information describing everything that fell into a black hole might not be lost inside its singularity, but was somehow encoded or painted onto its two-dimensional boundary. This idea was later strengthened by the work of Leonard Susskind and Gerard T. Hooft, who argued that this principle might not be limited to black holes. They proposed that it could be a fundamental property of the universe itself. Think of it like watching a movie on a flat, two-dimensional screen. The image appears to have depth, movement, and a full three-dimensional reality, but all of that information is actually stored in the pixels on the screen's surface. In the holographic universe, the cosmos is the movie, and the spherical boundary at the edge of the observable universe is the screen. All the information needed to describe every particle, every star, every person, and every event within our 3D world is actually stored on this vast, remote 2D surface. This isn't just a philosophical curiosity, it has concrete, testable consequences. One of the most intriguing predictions involves a fundamental limit to the information any region of space can contain. In a normal 3D world, the information capacity of a box would be expected to increase with its volume. The bigger the box, the more DVDs you could fit inside. But if the holographic principle is correct, the maximum amount of information that can be stored in that box is actually limited by the surface area of its walls, not the volume it encloses. It's as if the entire interior of the box is just a projection of data written on its inner surface. Experiments using incredibly precise lasers to measure the fabric of spacetime at the smallest scales are currently searching for the predicted pixelation or graininess that this fundamental information limit would create, a potential smoking gun for a holographic reality. The implications of this are enough to make your head spin. It suggests that the solidity and depth we experience are a kind of elaborate illusion. Your perception of being a three-dimensional being moving through a three-dimensional world is a magnificent trick played by the underlying data. This theory provides a potential path to unifying Einstein's theory of general relativity, which governs the very large, with quantum mechanics, which governs the very small, by showing how gravity in 3 dimensions might emerge from quantum processes on a 2-dimensional surface. We are left with a universe that is not just stranger than we imagine, but stranger than we can imagine, where the true nature of reality is a deeper, simpler, and flatter reality than we will ever directly perceive. This idea of an endlessly recycling cosmos brings us to another compelling vision of eternity, the cyclic model of the universe. Instead of a single, definitive beginning from nothing, this theory proposes a grand, rhythmic pulse to existence where universes are born, live, die, and are reborn in an infinite series. Imagine the cosmos not as a one-off explosion, but as a phoenix, continually rising from its own ashes in a cycle of cosmic renewal that stretches forever into the past and forever into the future. The core of this model often involves the universe eventually reversing its current expansion. After trillions upon trillions of years, when dark energy has diluted all matter and stars have long since burned out, the dominant force might shift. Perhaps gravity, acting over these immense timescales, finally wins out. The outward rush of galaxies could slow to a halt and then reverse, pulling everything back together in a catastrophic big crunch. All the matter and energy in existence would rush toward a single point of incredible density and temperature, seemingly obliterating everything. But in the cyclic view, this isn't an end, it's a reset button. The immense energy of this collapse becomes the seed for the next Big Bang, birthing a new universe from the remains of the old one. But here's where the theory gets truly fascinating. If each cycle were an exact, perfect replica of the last, we'd be stuck in an infinite loop of identical universes. The laws of physics would be the same every time, and the same stars, planets, and life forms would appear over and over. However, the unpredictable nature of quantum mechanics introduces a crucial element of change. During the violent transition between the Big Crunch and the subsequent Big Bang, tiny quantum fluctuations could be magnified. These random variations would act like a cosmic dice roll, slightly altering the fundamental constants of nature for the next cycle. Perhaps in one universe, the strength of the electromagnetic force is a fraction of a percent stronger. In another, the mass of a quark is minutely different. This means each new universe in the infinite sequence is not a perfect copy. It's a unique incarnation with its own slightly modified set of physical laws. Most of these universes would be stillborn or barren, their constant set in a way that prevents the formation of atoms, stars, or complexity. But every so often, through sheer chance, the quantum dice roll will produce a universe with the perfect Goldilocks conditions for life, a universe like ours. We are not a one in a million universe. We are a one in an infinite series universe, the latest in a long chain of cosmic epochs that had the right numbers to allow us to exist and ponder our own origins. This provides an elegant alternative to the multiverse for explaining fine-tuning. Instead of an infinity of different universes existing now, we have an infinity of different universes existing in sequence. Yet for all its grandeur, the idea of our reality as a simulation is not without its deep and troubling paradoxes. If we are living in a program, who or what is running it? We would have to assume the existence of a base reality, a universe where the laws of physics allow for such an advanced civilization to evolve and create simulations like ours. But then, what's to stop the beings in that reality from also being simulations themselves, created by an even higher form of intelligence? This leads to a dizzying infinite regress, a stack of simulated worlds within simulated worlds with no clear original universe. The very question of what is real becomes almost meaningless in this hall of mirrors. Furthermore, if our creators can manipulate the code, do we truly have free will, or are our choices just the result of a predetermined algorithm? The simulation hypothesis doesn't just challenge our place in the cosmos. It strikes at the very heart of consciousness, identity, and what it means to be alive. It transforms the universe from a majestic, physical expanse into a potentially artificial construct, a thought experiment on a scale so vast we are both the experiment and the experimenters. While we may never find definitive proof, the possibility alone irrevocably alters the lens through which we view our own existence, making every sunrise, every human connection, and every scientific discovery feel both incredibly precious and profoundly mysterious. But what if the branching of reality isn't just a passive, mechanical process governed by quantum equations, but is instead something deeply intertwined with our own minds? This brings us to a theory that pushes the boundaries of physics and philosophy into truly uncharted territory. The idea that consciousness itself might be the engine that drives the creation of parallel worlds. In this view, the hidden universes proposed by the many worlds interpretation aren't just out there in some external, objective reality. They are generated by the act of observation, suggesting that the very fabric of existence might be a mental construct as much as a physical one. To understand this, we need to revisit the central puzzle of quantum mechanics, the measurement problem. Why does a quantum particle exist in a blurry superposition of states until it is observed or measured, at which point it seems to snap into one definite reality? The traditional Copenhagen interpretation, developed by Niels Bohr and Werner Heisenberg, simply accepts this as a fundamental rule without explaining why the act of observation holds such power. It treats the conscious observer as a magical black box that collapses possibilities into a single fact. But this has always left a deeply uncomfortable question: what or who qualifies as an observer? Does it require a human scientist, a cat, a camera, a single-celled organism? The line is hopelessly fuzzy. The quantum many worlds of consciousness theory, sometimes associated with thinkers like John von Neumann and Eugene Wigner, offers a radical way out of this confusion. It proposes that the wave function never collapses at all. Instead, the moment a conscious mind becomes aware of a quantum system, that consciousness itself splits. The single stream of awareness diverges into multiple streams, each one perceiving a different outcome. There isn't one universe that splits, there is one mind that branches. The physical world remains in a superposition, but your conscious experience locks onto just one thread of that vast tapestry of possibility. You don't see the cat both alive and dead. Your awareness branches into one universe where you see it alive and feel relief, and another where you see it dead and feel grief. Both experiences are real, but they are now separated forever in the landscape of mind. This transforms the nature of reality from something objective and external into something profoundly participatory. The universe isn't a pre-recorded movie that we passively watch. It's an interactive story whose plot is determined by the questions we ask and the things we choose to look at. Your consciousness isn't a mere witness to reality. It is a co-creator carving a single, subjective path through an infinite field of potential. This means that the you listening to this right now is just one version of yourself, experiencing one specific outcome of countless quantum events that have occurred since you were born. Other versions of your consciousness are having completely different experiences, all equally valid and real from their perspective. The implications of this are nothing short of staggering for our understanding of identity and the self. It suggests that your conscious experience is not a single, continuous thread, but a constantly dividing river delta of awareness. The you of 5 minutes ago has already branched into countless versions of the you now, each having made different micro-decisions, noticed different details in their environment, and been affected by different quantum fluctuations in their brain chemistry. This idea resonates with certain interpretations of ancient Eastern philosophies, which have long proposed that the perceived world is an illusion or maya, and that the true nature of reality is a unified, undivided consciousness experiencing itself from an infinite number of viewpoints simultaneously. Of course, this theory is perhaps the most speculative we've encountered, sitting at the precarious intersection of quantum physics, neuroscience, and metaphysics. It raises formidable questions. If consciousness creates the branching, what about the universe before conscious life evolved? Did it exist in a nebulous state of pure potential? And how do we define consciousness in a way that avoids the same problems as defining an observer? Despite these challenges, it remains a compelling and fascinating perspective because it places our awareness, our perception, at the very heart of the cosmic mystery. It suggests that the search for hidden universes isn't just a journey outward into space, but an inward journey into the deepest nature of our own minds, where infinite realities might be waiting to be perceived. Yet for all its breathtaking scope, the bubble multiverse born from string theory's landscape would remain a static catalogue of possibilities, if not for a dynamic, ongoing cosmic process that gives it life. This brings us to the engine of creation itself, eternal inflation. Imagine that the initial explosive expansion of our universe, the Big Bang, was not a unique event, but merely the moment our local region of space-time transitioned out of a far more bizarre and energetic state. According to this theory, the vacuum of space is not truly empty. It is filled with a peculiar energy field known as the inflaton field. In most of the universe, this field has settled into a stable, low-energy state, which is why our cosmos expands at the relatively sedate pace we observe today. But what if, in some regions, this field never settled down? This is the core of eternal inflation. It proposes that the overall background state of the multiverse is one of frantic, exponential expansion. In this high-energy, false vacuum, space is stretching faster than the speed of light, pulling itself apart with unimaginable force. But this state is fundamentally unstable, like water that has been superheated past its boiling point. Just as bubbles of stable vapor suddenly form in superheated water, tiny pockets of the inflaton field can spontaneously quantum tunnel or fluctuate into a stable, low-energy state, a true vacuum. When this happens, that pocket stops inflating at the mad multiversal rate. It pinches off from the inflating background and begins its own, much slower expansion, becoming a separate, isolated bubble universe. Our entire observable cosmos, with all its hundreds of billions of galaxies, is likely the interior of just one such bubble that formed in the distant past. The truly mind-bending part is that this process is never ending. While our bubble universe formed and cooled, the inflating false vacuum outside of it continues to rage on, stretching eternally. And within that endlessly expanding sea of high-energy spacetime, new bubble universes are constantly being born. Each one forms with its own random set of physical laws, determined by how its local inflattened field settled. Some bubbles might have stronger nuclear forces, making stars burn out in a flash. Others might have extra dimensions unfurled, allowing for physics we can't conceive. Most would be utterly hostile to life as we know it, collapsing instantly or expanding into cold, empty voids. But in an infinite and eternal multiverse, every possible configuration dictated by the string theory landscape must eventually appear somewhere in the cosmic foam. We don't see these other bubbles because the space between us and them is that inflating false vacuum, stretching so rapidly that not even light could ever bridge the gap, forever isolating each universe in its own pocket of reality. Now, while these theories stretch our imagination across vast cosmic landscapes and branching timelines, another concept suggests that a hidden twin to our own reality might be far closer than we ever realized, separated not by immense distances, but by a fundamental reversal of nature's most basic rules. This is the mirror universe theory, an idea that posits the existence of a parallel cosmos where everything is flipped. A world where antimatter dominates, atomic spins are reversed, and perhaps even the arrow of time points in the opposite direction. To grasp this, we need to understand one of physics' most profound symmetries, CPT symmetry. This is considered a sacred rule in modern physics, stating that the laws of the universe should remain unchanged under the combined operations of charge conjugation C, parity P, and time reversal T. In simpler terms, if you take any physical process, reverse the charges of all the particles involved turning matter into antimatter, mirror the spatial coordinates so left becomes right, and reverse the flow of time, the process should still obey the same fundamental laws and be equally possible. Our universe is not perfectly symmetric under each of these individually. For instance, certain rare subatomic reactions show a slight preference for matter over antimatter, a puzzle known as baryon asymmetry. But under the full CPT transformation, perfect symmetry is believed to hold. This opens a stunning possibility. If our universe obeys CPT symmetry, then there should exist a perfect mirror image of it, a universe where all particles are replaced with their antimatter counterparts, the spatial dimension is mirrored, and time runs backward. From the perspective of an observer in that mirror universe, their world would seem perfectly normal and ours would appear to be the bizarre, reversed one. They would perceive time as flowing forward from their Big Bang, their stars would shine with the same light, and their physicists would devise the same laws. If we could somehow peer into this mirror world, we would see atoms with positrons orbiting antiprotons, forming antimatter molecules, antimatter planets, and antimatter life. A handshake between a person from our world and a person from that world would result in a catastrophic annihilation, as their matter and our antimatter, or from their perspective, their matter and our antimatter, would meet and obliterate each other in a flash of energy. The most mind-bending implication is the reversed arrow of time. In this mirror universe, entropy might decrease over what we perceive as time, leading to a world where broken cups assemble themselves, scattered ashes spontaneously form into logs, and lives are lived from grave to cradle. However, an observer living within that universe would not experience this as backward. Their conscious perception would be aligned with their local arrow of time. They would remember what we would call their future and anticipate what we would call their past. To them, their universe would appear just as ordered and logical as ours does to us. This isn't a universe running in rewind. It's a complete and self-consistent reality that is the CPT mirror of our own. The reason we don't interact with this mirror universe is that it is likely separated from us by more than just space. It may exist as a distinct domain that emerged from the same initial conditions as our own at the moment of the Big Bang, but with its properties perfectly inverted. We are forever isolated from each other, two parallel realities born from the same event, forever echoing each other in a perfect, silent symmetry across an unimaginable divide. But what if these other universes aren't just floating in an abstract landscape or splitting from our own, but are literally all around us, separated not by vast distances, but by dimensions we are physically unable to access? This brings us to a concept that takes the idea of hidden realities to a truly spatial level, the possibility of entire universes existing parallel to ours in the higher dimensional realm known as the bulk. According to string theory, the three dimensions of space and one of time that we experience are not the full extent of reality. The mathematics suggests there could be 10 or even 11 dimensions in total, with the extra ones curled up into shapes so incredibly tiny that they are invisible to us. But what if at least one of these extra dimensions is not small, but large, perhaps even infinite in size? This opens the door to the breathtaking possibility of a higher dimensional space, the bulk, that could be home to an entire archipelago of parallel worlds. Imagine our universe not as a solitary island in a void, but as one page in an impossibly massive book. This page, our home, has only length, width, and depth. To us, that is the entirety of existence, but the book itself has thickness, a higher spatial dimension that contains countless other pages, each one a separate, three-dimensional universe all stacked together. We are completely unaware of these other pages, these other universes, because everything that makes up our world, all the particles of matter and the forces that bind them, like electromagnetism and the nuclear forces, are irrevocably stuck to our own three-dimensional brain, short for membrane. We are like drawings on a page, unable to lift off the paper to interact with the drawings on the page above or below us, even though they might be mere millimeters away in the book's thickness. This model provides one of the most elegant solutions to a long-standing mystery in physics. Why is gravity so astonishingly weak compared to the other fundamental forces? A small refrigerator magnet can effortlessly overcome the gravitational pull of our entire planet. If gravity is so fundamental, why is it so feeble? The brain world hypothesis offers a stunning answer. Perhaps gravity is not weak at all. Maybe its strength is simply diluted because it is the only force not confined to our three-dimensional brain. The hypothetical particle that carries the gravitational force, the graviton, could be unique in its ability to leak off our brain and propagate through the full higher dimensional bulk. From our perspective, trapped on our page, this makes gravity's influence seem faint, as if its true strength is spread out across dimensions we cannot access or perceive. In the higher dimensional bulk, gravity might be as strong as the other forces, but we only experience a faint shadow of its full power. This leads to a profound and testable prediction. If other massive universes are floating on brains parallel to our own in the bulk, their gravity could subtly influence ours, just as you can feel the presence of a nearby object even with your eyes closed by its gravitational tug. Our universe might feel the presence of a hidden neighbor. The gravitational pull from a parallel brain could theoretically create strange anomalies in the motion of galaxies or contribute to the mysterious dark energy that is accelerating the expansion of our cosmos. Some cosmologists have even proposed that a dramatic collision between our brain and another in the distant past could have been the event that sparked our own Big Bang, seeding the hot, dense state from which our universe evolved. In this view, the birth of our cosmos wasn't an explosion from nothing, but a colossal collision in a higher dimensional space, a cosmic car crash whose echo we perceive as the beginning of time itself. The sheer scale of this idea is humbling. Every point in our three-dimensional space could have an entire other universe just a minuscule distance away in a direction we cannot point to, a dimension we cannot move in. Civilizations could rise and fall, stars could explode, and entire histories could unfold literally right next to us, forever separated by a fundamental gap in the nature of reality itself. It transforms the cosmos from a vast emptiness into a crowded, multi-layered metropolis of worlds, each one humming with its own activity, forever hidden from view but perhaps faintly connected by the gentle, universal hand of gravity. Now let's journey to the very edge of known physics, to a place of such unimaginable density that the very fabric of space and time is torn apart. We're talking about the singularity at the heart of a black hole. And here we encounter a hypothesis so audacious it redefines our place in the cosmic order, the black hole universe hypothesis. This theory proposes that these points of infinite density are not in points of destruction, but rather portals of creation. That each black hole is the seed for an entirely new, expanding universe, and that our own cosmos may itself be the interior of a black hole existing in a far larger parent universe. To grasp this, we need to reframe our understanding of a black hole's interior. According to Einstein's general relativity, anything that crosses the event horizon is inexorably pulled toward the central singularity. From our external perspective, time for that infalling matter appears to slow to a halt at the horizon, but from its own perspective, it continues inward. The classic view is that it's crushed out of existence, but what if that's not the final chapter? Some physicists, like Nikodem Poplawski, have proposed that the extreme conditions within a black hole could trigger a bounce, a quantum gravitational repulsion that is so powerful it reverses the collapse into a new, outward expansion. In this scenario, the singularity isn't a dead end, it's a cosmic reset button. The matter and energy that fell in become the hot, dense primordial material for a new Big Bang, birthing a baby universe within the black hole. This new universe would be entirely separate from its parent. Its Big Bang is our black hole's formation, and its entire future evolution, the formation of galaxies, stars, and planets, unfolds within the confines of the event horizon, which from the inside would appear to be an immeasurably vast and expanding boundary. Crucially, the laws of physics in this new universe could be different from those in the parent. The process of collapse and bounce might randomly alter the fundamental constants, creating a new set of physical laws. This provides a stunningly elegant mechanism for the multiverse. Every black hole in every universe could be spawning a new cosmos with its own unique properties, leading to an infinite fractal nesting doll of realities. This leads to the inevitable mind-bending question: if universes can be born inside black holes, could our own universe be the interior of one? It's a possibility that is both humbling and awe-inspiring. The Big Bang shares remarkable similarities with a black hole singularity, and point of immense density from which everything we see expanded. Perhaps our entire cosmic history is playing out inside a black hole that formed in some larger meta-universe. In that parent reality, our universe would appear as a gravitational anomaly, a region of incredibly dense mass-warping spacetime. The event horizon of that black hole would be the ultimate boundary of our reality, a spherical shell from which nothing, not even light, could escape to communicate with the world outside. We are forever isolated within our own cosmic Matryoshka doll, unaware of the greater structure that contains us. This hypothesis even offers potential explanations for some of our universe's deepest mysteries. For instance, the observed uniformity of the cosmic microwave background radiation, the faint afterglow of the Big Bang, is a puzzle. How did regions of the universe too far apart to ever have been in contact manage to reach the same temperature? If our universe was born from a black hole, the initial conditions for the bounce would have been set in a highly ordered state by the immense gravitational forces of the collapse, potentially explaining this smoothness from the very beginning. While still a highly speculative idea, the black hole universe hypothesis transforms these enigmatic voids from monstrous destroyers into potential creators, suggesting that the cycle of death and rebirth might be the fundamental engine driving all of existence on the grandest scale imaginable. But if the black hole hypothesis suggests new universes are born from collapse, another theory proposes that the seeds of entire realities might exist in a state of potential all around us, embedded in the very fabric of the quantum world. This brings us to a concept that pushes the many worlds interpretation to its ultimate conclusion. The idea that quantum superposition isn't just about particles, but about entire universes existing in a blurred state of possibility until an observation locks one into place. This isn't just about a cat being alive and dead. It's about two complete, independent cosmoses, one with a living cat and one with a dead one, existing simultaneously in a state of overlap, waiting for a conscious mind to force a choice. We have to go back to the classic thought experiment that highlights the strangeness of the quantum realm, Schrödinger's cat. A cat is placed in a sealed box with a radioactive atom, a Geiger counter, a hammer, and a vial of poison. If the atom decays, the Geiger counter triggers the hammer to break the vial, killing the cat. According to quantum rules, until someone opens the box and looks inside, the radioactive atom exists in a superposition. It has both decayed and not decayed. Therefore, the cat is also in a superposition, both alive and dead at the same time. The standard Copenhagen interpretation says that the act of observation by a conscious being collapses this wave function of possibilities, forcing the universe to choose one definite outcome, either a living cat or a dead one. The quantum superposition universe's theory takes this a step further. It suggests that the two possibilities aren't just abstract probabilities in a single universe. They are two fully realized parallel universes that are temporarily in a state of quantum coherence with each other. In this view, the moment the experiment is set in motion, reality doesn't split, but rather, two complete and separate universes begin to exist in a ghostly, overlapping state. Both universes are physically real, each containing an entire, consistent world where the events in the box have a single outcome. However, they are not yet completely independent. They are still quantumly entangled, their fates linked. It is only the act of measurement, the opening of the box, that severs this final connection, decohering the two universes and causing them to snap apart into two distinct, non-communicating timelines. The observer doesn't create one reality and destroy the other. They simply become aware of which branch of reality they are now permanently trapped within, while the other branch continues on its own separate path, forever out of reach. This resolves the uncomfortable magic of the Copenhagen interpretation, which never adequately explained why observation holds such power. Instead of a mysterious collapse, we have a process of decoherence, where the interaction between a quantum system and its environment, such as photons bouncing off the box, irreversibly separates the once connected possibilities. The role of the conscious observer is not to collapse the wave function, but to become entangled with it. Your brain, your memories, and your very sense of self become correlated with one specific outcome. You don't cause the split, you simply inherit its consequences, becoming the version of you that saw the cat alive, while another version of your consciousness, equally real, becomes the one that saw it dead. The implications of this are staggering when you scale it up from a cat in a box to the universe as a whole. It suggests that in the very first moments after the Big Bang, the entire cosmos may have existed in a superposition of many possible initial states. Perhaps the fundamental constants weren't fixed immediately, but existed in a blurred cloud of potential values, a gravitational constant that was both strong and weak, a cosmological constant that was both high and low. The first quantum interactions, the first particles bumping into each other, would have triggered a massive, universal decoherence, locking in one specific set of physical laws for our universe while simultaneously spawning other universes where different constants became permanent. Our entire cosmic history, from the formation of the first atoms to the evolution of life, might be just one single possibility that was actualized from an infinite quantum menu at the dawn of time, with every other option playing out in its own parallel cosmos. But what if this entire cosmic landscape of possibilities, from the bubbling multiverse to the branching quantum worlds, is grounded in something even more fundamental? What if reality isn't just described by mathematics, but actually is mathematics? This brings us to one of the most profound and elegant ideas on our list, the mathematical universe hypothesis, championed by physicist Max Tegmark. This theory proposes a breathtakingly simple yet radical answer to the question of what existence truly is. It states that our physical reality isn't just modeled or approximated by mathematics, it is a mathematical structure. And by extension, every self-consistent mathematical structure doesn't just describe a possible universe. It is a real, physical universe existing somewhere in the grand multiverse of all possible computations. To understand this, let's first consider how we use math to describe the world. We write down equations for gravity, for the motion of planets, for the behavior of subatomic particles. The incredible success of this endeavor has led physicist Eugene Wigner to famously call it the unreasonable effectiveness of mathematics in the natural sciences. We treat the mathematics as a language, a tool we invented to map onto a physical reality that exists independently of it. The mathematical universe hypothesis flips this completely on its head. It suggests the tool isn't just mapping the reality, the tool is the reality. The mathematical structure doesn't describe the universe is the physical instantiation of that mathematical structure. Think of it like a video game world such as the universe of Minecraft. That world is entirely defined by its code, its algorithms, its rules for how blocks interact, its laws of physics. The code isn't a description of the Minecraft world. The code is the Minecraft world. Without that underlying mathematical structure, the world doesn't exist. In the same way, Tegmark argues, our universe is defined by a specific, immensely complex mathematical structure. All the things we perceive, particles, forces, galaxies, even our own consciousness, are not primary entities. They are simply patterns or emergent properties that arise from the underlying equations playing themselves out. We aren't living in a universe that runs on math, we are patterns within the math itself. This leads to the truly staggering implication of the hypothesis. If our universe is one particular mathematical structure, what about all the other possible mathematical structures? Mathematics is a vast and infinite landscape. There are structures that describe the rules of chess, structures that define different geometries with 4 spatial dimensions, structures for universes where time runs in 2 directions or where the number pi has a different value. The mathematical universe hypothesis grants all of these structures the same ontological status, the same level of realness. Every single self-consistent mathematical structure corresponds to a physically existing universe. This creates the ultimate multiverse, a level 4 multiverse in Tegmark's classification, which encompasses all the other multiverses we've discussed. The bubble universes, the branching quantum worlds, the brain worlds, they all become specific subsets of this vast, all-encompassing mathematical multiverse. Some of these mathematical universes would be barren and simple, perhaps containing nothing but empty space obeying a single, simple equation. Others would be wildly complex and chaotic, changing in ways too fast for any form of structure to arise. And a very special few, like our own, would have mathematical properties that allow for the emergence of complex, self-aware substructures, beings like us, who can observe the universe and even begin to decipher the mathematical patterns that we are made of. In this view, the reason our universe appears so finely tuned for life isn't a coincidence. It's a selection effect, much like the bubble multiverse, but on an even grander scale. We can only find ourselves in one of the rare mathematical structures that is complex enough to contain observers. This idea is both incredibly powerful and deeply humbling. It removes the need for any external, unexplained baggage to reality. There is no mysterious, physical stuff that the math is describing. There is only the math. It answers the ancient question of why there is something rather than nothing, because nothing is mathematically unstable, and the rich, complex structures of mathematical existence are inevitable. It is a vision of a cosmos that is ultimately abstract, eternal, and immutable. The laws of physics aren't laid down by some creator. They are simply the properties of the particular mathematical structure we happen to inhabit. And as we peer deeper into the fabric of reality, using tools like quantum mechanics and general relativity, we aren't discovering the laws of nature. We are discovering the mathematical shape of our own existence. While many theories point to hidden dimensions or branching timelines to explain the cosmos, another idea suggests the answers we seek are not hidden at all, but are written in the electrified gas that makes up most of the visible universe. This is the plasma universe theory, an alternative cosmology that challenges some of the most fundamental assumptions of modern astrophysics. It proposes that the dominant force shaping the large-scale structure of the cosmos is not gravity, but electromagnetism, operating across vast seas of plasma, a state of matter so energetic that atoms are ripped apart into a soup of free electrons and atomic nuclei. To grasp the scale of this idea, we must first recognize that over 99% of the observable universe, from the shimmering tendrils of nebulae to the scorching atmospheres of stars, is in this plasma state. It is often called the fourth state of matter, and it is anything but placid. Because the electrons and nuclei are charged, plasma is an excellent conductor of electricity. And where you have moving electric charges, you generate magnetic fields. This creates a complex, dynamic dance where electric currents and magnetic forces can shape plasma into intricate structures like filaments, cells, and double layers, all while generating powerful electromagnetic forces that can accelerate particles to nearly the speed of light. Proponents of the plasma universe, such as physicist Hans Alfvén, who won a Nobel Prize for his work in magnetohydrodynamics, argue that these electromagnetic processes, which we can observe and replicate in laboratories on Earth, are sufficient to explain the formation and behavior of galaxies and galaxy clusters without the need for unseen, mysterious components like dark matter. For instance, the rotation curves of galaxies, the observation that stars at the outer edges of galaxies orbit just as fast as those near the center, which is the primary evidence for dark matter, could instead be explained by the magnetic fields permeating the galactic plasma. These immense magnetic fields could provide an additional, non-gravitational force that shapes the motion of stars. Similarly, the immense filamentary structures of galaxies stretching across billions of light years, often described as the cosmic web, bear a striking resemblance to the delicate, filamentary structures seen in plasma discharge experiments, suggesting a similar underlying electromagnetic architecture. This view paints a picture of a universe crisscrossed by gigantic, flowing electric currents, moving along cosmic magnetic field lines that act as transmission lines for energy across unimaginable distances. In this model, stars are not isolated nuclear furnaces powered by gravity alone, but rather focal points in a vast galactic circuit. They might be more accurately understood as immense glowing electrodes, with their energy output influenced by the electrical currents flowing into them from the surrounding plasma in space. This could potentially account for some of the more energetic and puzzling stellar phenomena that are difficult to explain with standard models. Even quasars, the intensely bright cores of distant galaxies, could be explained not as supermassive black holes accreting matter, but as tremendous concentrations of electrical energy, cosmic lightning bolts focused on a single point, pouring power out from the circuits of the galaxy. The most profound implication of the plasma universe theory is that it suggests our cosmos might not be governed by a single, uniform set of physical laws. In the standard cosmological model, the laws of physics are assumed to be constant everywhere. But if electromagnetic forces dominate in some regions, the local conditions of the plasma could create environments where phenomena play out by different rules. A region of space with an extremely strong magnetic field or a powerful electric current could behave in ways that would be completely impossible in the relatively placid, neutral space around our own solar system. In essence, different cosmic environments could operate under different effective laws of physics, not because the fundamental constants change, but because the dominant forces shaping events are entirely different. This introduces a new kind of hidden universe, not one separated by dimensions or branes, but one hidden in plain sight, a universe of electromagnetic structures and forces so vast we are only beginning to recognize their true influence on the cosmic stage. While many theories propose a multiverse existing alongside our own or branching from quantum choices, another idea offers a different kind of eternity, an infinite, repeating cycle where the death of one cosmos gives birth to the next. This is conformal cyclic cosmology, a profoundly elegant and radical theory proposed by the Nobel Prize-winning physicist Roger Penrose. It suggests that our universe is not the first and will not be the last, but is merely one in an endless sequence of cosmic epochs or eons, each one arising from the ashes of its predecessor in a cycle without beginning or end. To grasp this beautiful idea, we must first confront the ultimate fate of our universe. According to the standard model, the relentless expansion driven by dark energy will lead to a heat death. Over trillions of years, all stars will burn out, black holes will evaporate via Hawking radiation, and matter itself will eventually decay. The universe will approach a state of absolute uniformity, a vast, cold, and empty void where the temperature plunges to near absolute zero and nothing ever happens again. It seems like a definitive, bleak, and final end. But Penrose looked at this desolate future and saw not an end but a transformation. He realized that in this state of ultimate emptiness and stillness, a miraculous thing happens. The universe, in a sense, forgets its scale. This is where the key concept of conformal rescaling comes in. In physics, conformal transformations are those that change the scale of things but preserve their angles and shapes. Imagine a detailed map. You can shrink or enlarge the map, but the precise angles at which roads intersect remain the same. Penrose's genius was to apply this concept to the entire cosmos. In the far, far future, when the universe is an endless, flat sea of massless radiation and ghostly particles, the concept of distance and duration becomes meaningless. There is no matter to provide a scale, no clocks to tick off time. In this bizarre state, the universe becomes conformally invariant. It has no discernible size or age. An infinitely vast, infinitely old empty universe is mathematically identical to an incredibly tiny, incredibly young one, and this is the breathtaking leap. Penrose proposes that the infinite future of one eon can be seamlessly connected, or conformally rescaled, to the infinitesimal, high-energy singularity of the next. The ultimate, cold, expanded state of our universe becomes the hot, dense, contracted Big Bang of the next one in the cycle. There is no mysterious creation from nothing. Instead, the end smoothly transitions into a new beginning. Each eon starts with its own hot Big Bang, expands and evolves over countless eons, and then dies its heat death, only to reset and give birth to the next universe in an infinite loop. Our entire cosmic history, from the first second to the last evaporated black hole, is just one turn of an eternal cosmic wheel. One of the most stunning and testable implications of this theory involves the very beginning of our own universe. The standard Big Bang model has a problem. Why was the early universe in such a state of incredibly low entropy, so perfectly ordered and smooth that it allowed for the formation of galaxies and life? This is like finding a room that has been meticulously cleaned and prepared. It implies a previous state of affairs. Conformal cyclic cosmology provides an elegant answer. The low entropy of our Big Bang didn't come from nowhere. It was an inheritance. It was the natural consequence of the fact that the universe that came before ours ended in a state of maximum smoothness and emptiness. The serene, uniform end of the previous eon directly provided the serene, uniform beginning for ours. But if information is lost in the transition, how could we ever know? Penrose and his colleagues have searched for a potential fingerprint, a ghostly echo from a universe that existed before our own. They reasoned that if violent, large-scale events occurred in the previous eon, like the collisions of supermassive black holes, the gravitational waves generated by those cataclysms could have left an imprint on the structure of spacetime that carried through the conformal rescaling. This imprint might be visible in the cosmic microwave background, the afterglow of our own Big Bang. They have identified strange, concentric circular patterns of temperature variation in the SIMBI data, which they call Hawking points, named after Stephen Hawking. These points, they suggest, could be the faint but observable signatures of the final bursts of energy from evaporating black holes in the eon that came before ours, the last dying breaths of a previous cosmos, etched onto the first light of our own. While this evidence remains controversial and hotly debated within the cosmology community, it represents a breathtaking possibility that we might one day hold a fossil not from a prehistoric age on Earth, but from an entire universe that existed before time as we know it began. But if the grand, eternal cycles of conformal cosmology stretch our conception of time to its limits, another theory brings the act of creation down to the smallest possible scale, suggesting that entire universes could be popping into existence all around us, born from the seemingly empty void itself. This is the astonishing proposition of virtual particle universes, an idea that takes a well-known quantum quirk and scales it up to the most cosmic proportions imaginable. To understand this, we must first venture into the bizarre world of the quantum vacuum, which is anything but empty. What we perceive as true nothingness is actually a seething, chaotic foam of potentiality, where particles and energy fluctuate in and out of existence in a frantic dance governed by the Heisenberg uncertainty principle. This principle tells us that we can never know both the exact energy of a system and its exact duration at the same time. This isn't a limitation of our measuring devices, it's a fundamental property of reality. This uncertainty allows for a profound loophole in the conservation of energy, but only for an incredibly brief moment. Imagine borrowing a large sum of money, but you have to pay it back almost instantly. In the quantum world, this borrowing is constant. These fleeting particles are known as virtual particles. They flicker into existence in particle-antiparticle pairs and then almost immediately annihilate each other, returning the energy to the vacuum. We know this is real because we can observe its effects, such as the Casimir effect, where two metal plates placed extremely close together in a vacuum are pushed together by the pressure of these virtual particles popping off outside them. Now take this concept and inflate it to a cosmic scale. What if, instead of a single particle-antiparticle pair, a quantum fluctuation borrowed enough energy to create not just a handful of particles but an entire universe? This is the core of the theory. In the unimaginably dense energy of the primordial vacuum, perhaps at the Planck scale, a random fluctuation could have tunneled into a new state, a bubble of false vacuum that contained within it all the potential energy needed for a cosmic expansion. This bubble would be our universe in its earliest, most nascent state. Most of these fluctuations would be stillborn. They would borrow the energy, begin to inflate, but then collapse back into the quantum foam almost immediately, their energy debt called in before they could achieve stability. They would be like tiny, failed bubbles in a boiling pot, appearing and vanishing in a fraction of a nanosecond. But through sheer random chance, one fluctuation might have been just large enough or lasted just long enough to cross a critical threshold. Once it expanded to a certain size, the energy contained within its own structure could have become self-sustaining, allowing it to pay back its energy debt to the quantum vacuum over the incredibly long timescale of its own expansion and evolution. This one successful fluctuation would no longer be virtual. It would become real, pinching off from the background quantum foam to become its own independent, expanding spacetime continuum, a universe that could eventually cool, form galaxies, and give rise to conscious life. In this view, our Big Bang was not a unique event, but a statistical inevitability. In an eternal, chaotic quantum vacuum, every possible fluctuation must eventually occur. Given an infinite amount of time, a fluctuation that creates a stable, long-lasting universe isn't just possible, it's guaranteed. We are the product of the ultimate quantum accident, a random roll of the cosmic dice that paid off, transforming a fleeting virtual possibility into the rich, physical reality we call home. Yet for all its mathematical elegance and cosmic grandeur, this journey into hidden realities leads us to a profoundly intimate and unsettling question. What if the universe is not an external, objective entity at all, but a construct that emerges from within? This brings us to a theory that stands at the farthest frontier of physics and philosophy, a place where the observer and the observed become one. It is the idea that consciousness is not merely a passenger in the cosmos, but its fundamental architect, that each mind, each point of awareness, generates its own unique reality, making hidden universes not distant realms in space but private worlds of perception. This concept, often called idealism in philosophy, radically inverts our standard view of reality. Instead of a physical universe that somehow, mysteriously, gave rise to conscious beings who can observe it, this view proposes that consciousness is the primary, fundamental substance of existence. The physical world, the stars, the planets, the chair you're sitting on, is a manifestation, a kind of shared dream or mental projection arising from a deeper field of mind. In this model, there isn't one single objective universe out there. Instead, there are as many universes as there are conscious perspectives, each one a unique configuration of reality filtered through and shaped by a particular point of view. To grasp this, consider the simple act of looking at a tree. The standard scientific story is that photons of light bounce off the tree, enter your eye, are converted into electrical signals, and interpreted by your brain to create the experience of seeing a tree. But idealism asks a deeper question. How do those electrical signals, mere pulses of energy, ever transform into the rich, green, textured experience of a tree? This gap between physical processes and subjective experience is known as the hard problem of consciousness, and materialism has no satisfactory answer for it. The consciousness-created universe theory proposes a solution. The tree, and indeed the entire physical world, is that experience. It exists as perception itself, not as an independent object causing perception. This doesn't mean reality is solipsistic or that we are all alone in our own private bubbles. Proponents suggest that our individual conscious experiences are likely facets of a much larger, universal consciousness, much like waves are individual expressions of a single ocean. We are all dreaming the same dream, so to speak, and the consistency of the physical laws we observe is a result of shared rules within that dream. However, subtle differences in perception could mean that your universe and my universe, while overwhelmingly similar, are not perfectly identical. The hidden universes, then, are not separated by light years or brains, but by the unbridgeable gap between your subjective experience and mine. Your red might be my blue, your flow of time might feel different to you than mine does to me. We can never truly know because we cannot swap consciousnesses to compare notes. This perspective finds surprising resonance with some interpretations of quantum mechanics, particularly the role of the observer. The famous double-slit experiment shows that a particle seems to behave as a wave of possibilities until it is observed, at which point it collapses into a definite particle. The consciousness-created universe theory takes this a step further. suggesting that it is not the measuring device but the act of conscious observation itself that completes the reality, that forces the infinite possibilities of the quantum wave function to crystallize into a single, concrete event. In this view, the universe remains in a fluid, potential state until a mind looks at it, and in that moment a specific reality is born. Every glance, every measurement is an act of creation, carving a single world out of an infinite sea of maybes. This transforms our role in the cosmos from passive spectators to active participants, continuously weaving the tapestry of reality with every thought and every observation. We are not just discovering the laws of the universe, we are, in the most literal sense, dreaming them into being. But what if the flow of time, that most fundamental rhythm of our existence, is nothing but a powerful illusion? We feel time passing, we remember the past and anticipate the future, yet physics tells us that this experience might be a grand trick of perception. This brings us to a theory that completely reimagines the nature of reality itself, the idea of time-slice universes. In this breathtaking model, there is no flowing river of time. Instead, every single moment, the Big Bang, the fall of the dinosaurs, you reading this sentence, and the heat-death of the cosmos exists eternally and equally, frozen in place like frames in a cosmic film reel. Our conscious journey from one moment to the next is merely an illusion of movement, a light scanning across these frozen frames, creating the undeniable sensation of a past that is gone and a future that is yet to come. This concept is deeply rooted in Einstein's theory of relativity, which fused space and time into a single, four-dimensional continuum called spacetime. In this block universe model, the cosmos is a static, unchanging, four-dimensional block where every event has its own coordinates. Your birth, your first day of school, and your last day on Earth are all fixed points in this immense structure, just as real and concrete as the cities of Paris and Tokyo are fixed points on the globe. The feeling that the past is gone and the future doesn't yet exist is, from this perspective, a kind of parochial bias of our consciousness. We are like a driver who believes only the spot directly under their car is real, while the road behind has vanished and the road ahead is unformed. In reality, the entire highway exists at once. The time-slice universe theory takes this block model and pushes it to its ultimate conclusion. It proposes that each distinct moment or time slice is its own separate parallel universe. In this view, there is a universe for the exact moment a Tyrannosaurus Rex took its last breath. There is a separate, complete universe for the moment you were born. And there is another universe for the moment, far in the future, when the last star in the cosmos winks out of existence. All these moments are real, and they are all happening now in the grander scheme of things. They don't cause each other, they just are. The laws of physics that connect them are not about one moment creating the next, but about the harmonious mathematical relationship between adjacent frames in the block. This completely transforms our understanding of free will and destiny. If every possible moment already exists in the block, then every choice you will ever make is already set in stone. The version of you that chose to watch this video and the version that decided to do something else both exist as separate, parallel time-slice universes. Your feeling of making a choice is simply your consciousness inhabiting one of these predetermined tracks. This doesn't make your experiences any less real. It just means that the entire tapestry of your life is woven and complete from a perspective outside of time. You are living out your unique, fixed path through the frozen landscape of eternity. The profound implication is that death, as we fear it, may not exist. The you that is reading this sentence, the you that is 10 years old, and the you that is elderly all exist with equal reality. No moment is ever lost. The past isn't a fading memory, it is a place, a complete universe that still exists. This offers a strange kind of immortality, where every joy, every triumph, and every moment of love is preserved forever in its own self-contained reality, playing out on an endless loop in the vast museum of spacetime. We are not travelers moving through time. We are permanent residents of a single, eternal moment, with the illusion of movement created by the narrow focus of our conscious awareness. Yet if the concept of a consciousness-generated reality challenges our very sense of an objective world, our next theory proposes a universe where objectivity is baked into the fabric of existence, but in a state of such profound multiplicity that it defies our everyday intuition. We arrive at one of the most ambitious and technically complex ideas on our list, the quantum gravity multiverse. This concept emerges from the greatest unsolved problem in all of physics, the monumental struggle to reconcile the chaotic, probabilistic rules of the quantum world with the smooth, geometric curvature of Einstein's general relativity. The stunning suggestion is that the very act of unifying these two pillars of physics may require us to accept a reality where multiple, complete universes with different space-time geometries are not just possible, but are all equally real and existing simultaneously. To appreciate this, we need to understand the nature of the conflict. General relativity gives us a breathtakingly elegant description of gravity. It's not a force in the traditional sense, but rather the curvature of space-time itself. Planets orbit stars not because they are being pulled by an invisible string, but because they are following the straightest possible path through a four-dimensional landscape warped by the star's mass. This theory works flawlessly on large scales, predicting the motion of galaxies and the bending of light around black holes. Meanwhile, quantum mechanics provides an incredibly accurate description of the other three fundamental forces: electromagnetism and the nuclear forces operating at the subatomic level. Here, reality is fuzzy and probabilistic, with particles being waves and possibilities until observed. The problem is that these two theories speak completely different mathematical languages and make contradictory assumptions about reality. When we try to combine them to understand gravity at the quantum level, like at the center of a black hole or the first moment of the Big Bang, the mathematics utterly breaks down, producing nonsensical infinities. For decades, physicists have been searching for a theory of quantum gravity, a single framework that can describe all forces under one roof. And one of the most promising, yet puzzling, suggestions from this search is that such a theory might not describe a single history for the universe, but rather a sum over all possible histories. This is the core of the quantum gravity multiverse. In this view, the universe does not have one specific space-time geometry. Instead, it exists in a quantum superposition of every possible way that space-time could be curved and structured. There isn't one universe with 4 dimensions. There is a probability-weighted blend of universes with 3 dimensions, 4 dimensions, 10 dimensions, and every conceivable configuration in between. Each possible geometry is a complete, self-consistent universe with its own gravitational properties. In one branch of this superposition, gravity might be slightly stronger, causing stars to burn out faster. In another, the number of extended spatial dimensions might be greater, allowing for complexities of form and motion that we cannot even picture. Our familiar 4-dimensional cosmos with its specific curvature is just one single thread in this immense tapestry of possible space-time fabrics. We never perceive this bewildering multiplicity because of a process called decoherence. The instant a measurement is made or an interaction occurs, this blurred superposition of possible universes collapses into a single classical reality that we can observe. But according to the quantum gravity interpretation, the other geometric possibilities don't vanish. They simply become decoherent, branching off into their own separate parallel realities. This provides a potential mechanism for the origin of the bubble universes we discussed earlier. The initial quantum fluctuation that gave rise to our cosmos wasn't a single event, but a superposition of every possible fluctuation, each birthing a universe with a different vacuum energy and therefore a different space-time geometry. Our universe, with its particular curvature and laws, is the one we find ourselves in, while an infinity of others with vastly different gravitational properties were actualized alongside it. This idea finds a powerful expression in the Hawking's no-boundary proposal and the path-integral formulation of quantum mechanics, which essentially calculate the probability of our universe by summing over every possible way it could have begun and evolved. It suggests that the quest for a single, unique theory of everything might be misplaced. Instead, the fundamental law could be a mathematical rule that allows for every possible self-consistent universe to somehow exist, with our own being just one likely outcome in an endless landscape of physical reality. We are left with a cosmos that is not merely expanding or branching, but one that is fundamentally fuzzy at its core, a quantum superposition of all possible worlds, waiting for the act of observation to crystallize one specific gravitational reality into being. But what if these countless universes are not truly separate, but are instead woven together from the same underlying fabric of information, like different scenes projected from a single master film reel? This brings us to a theory that merges the mind-bending implications of the holographic principle with the vastness of the multiverse concept. The holographic multiverse suggests that not only could our three-dimensional reality be a projection, but that an entire ensemble of universes might be encoded on a single, shared boundary surface, a common cosmic hard drive from which all realities are rendered. To understand this, we must first revisit the core idea of the holographic principle, which emerged from the study of black holes. It tells us that all the information describing everything within a volume of space, every particle, every force, every event, can be thought of as encoded on the two-dimensional surface area that encloses that volume. It's as if the three-dimensional world we experience is a projection, much like a hologram that appears to have depth but whose information is stored on a flat, two-dimensional plate. Now take this concept and scale it up to its ultimate conclusion. If our universe is holographic, then the entire observable cosmos, with its hundreds of billions of galaxies, could be a projection from data stored on a vast, spherical boundary at the edge of our observational horizon. The holographic multiverse theory pushes this idea even further. It proposes that this foundational boundary surface might not be unique to our universe. Instead, it could be a kind of fundamental canvas upon which the information for multiple, even infinite, universes is written. Each universe would correspond to a different set of data, a different configuration of bits on this shared cosmic surface. Our universe, with its specific laws of physics and history, would be one particular projection from this data. A parallel universe with slightly different constants or an entirely alternate history would simply be a different projection from a different set of information on the same underlying surface. They wouldn't be separate bubbles floating in a void. They would be different movies playing from the same immense hard drive, all derived from the same source but expressing vastly different realities. This provides a stunningly elegant and unified vision of the multiverse. Instead of an ungainly collection of disconnected domains, the entire multiverse becomes a single, coherent mathematical structure. The bewildering diversity of possible universes, some with stronger gravity, some with 5 spatial dimensions, some where the dinosaurs never went extinct, isn't a chaotic mess. It is simply the complete set of all possible data configurations that can be written on the boundary. The laws of physics in each universe are not arbitrary. They are the emergent properties of how that particular dataset is structured and projected into a volumetric reality. This means that the search for a fundamental theory of everything might not be a search for the laws of our universe alone, but for the master code that governs the entire library of possible datasets on the boundary, from which every conceivable universe can be projected. The most profound implication of this idea is a radical redefinition of location and separation. In most multiverse models, other universes are far away, separated by unimaginable distances or hidden in higher dimensions. But in the holographic multiverse, another reality could be right here, overlapping with our own in the same three-dimensional space. How is that possible? Because both realities are just different projections from the same source. They are like two different radio stations broadcasting on different frequencies. They occupy the same space but do not interact because they are decoding the underlying signal in completely different ways. A particle from another universe could, in theory, be right here in this room, but it belongs to a different projection, a different set of data being read out from the boundary, and is therefore completely invisible and intangible to us. This suggests that the hidden universes we've been searching for might not be distant at all. They might be all around us, layered atop our own like ghostly echoes, forever separated not by space but by information. Now, if these scientific and physical theories stretch the boundaries of what seems plausible, prepare to venture into a realm where philosophy itself challenges our most basic intuitions about what is real. This brings us to a concept that is both intellectually audacious and profoundly simple: modal realism, as proposed by the philosopher David Lewis. Lewis put forward a staggering idea: that every single possible world that can be coherently imagined is not just a theoretical concept, but a concrete, physical reality, every bit as real as the one we are in right now. In this view, the multiverse is not just a collection of universes with different physical laws. It is the complete set of all logical possibilities, a plenitude of existence where nothing that can happen fails to happen somewhere. To grasp the sheer scale of this idea, we must first understand what Lewis meant by a possible world. It is any way that a world could be, as long as it is logically consistent and free from contradiction. A world where gravity is twice as strong is a possible world. A world where Napoleon won the Battle of Waterloo is a possible world. A world where you are reading this script in a library on Mars is a possible world. Lewis's radical claim was that these are not mere fictions or useful tools for thought experiments. They are actual, tangible places, isolated from each other in a vast multidimensional space, each one a universe unto itself, operating under its own local laws. We just happen to inhabit one of these countless worlds, which we call the actual world. But from the perspective of someone in another possible world, their world is the actual one, and ours is just another possibility. There is no privileged center to this reality. All worlds are ontologically equal. This leads to some truly mind-bending conclusions. It means that every work of fiction, every myth, every daydream, and every counterfactual thought you've ever had describes a real world. The world of Shakespeare's Hamlet is real. The world of Greek mythology is real. A world entirely populated by singing teacups is real, as long as it is logically possible for such a world to exist. The only things that are not real are impossible things like a square circle or a married bachelor, because they violate the fundamental rules of logic. For Lewis, the word actual doesn't refer to a special kind of reality. It is merely an indexical term like here or now. We call our world actual because we are in it, just as we call our location here. For a person in another possible world, their world is actual, and ours is just a distant possibility they might contemplate. But why adopt such a seemingly extravagant view? Lewis argued that modal realism is actually the simplest and most powerful explanation for a host of philosophical problems. We constantly use the language of possibility and necessity. We say things like, "I could have taken a different job," or "it is necessary that 2 + 2 = 4." What do these statements mean? Lewis provided a clean, elegant answer. To say that something is possible is to say that it is true in at least one possible world. To say something is necessary is to say it is true in all possible worlds. This eliminates the need for fuzzy metaphysical concepts. It grounds our talk of possibilities in concrete, existent realities. The reason you could have taken a different job is because there is a very real world, similar to this one up until that decision point where a version of you did exactly that. The reason 2 plus 2 equals 4 in every universe is not because of a mysterious mathematical truth, but because any world where it didn't would be logically incoherent and therefore impossible. In this framework, the multiverse becomes the ultimate foundation for logic, mathematics, and even truth itself. But if the black hole universe theory suggests new cosmoses are born within these gravitational giants, a related idea takes this concept a step further, proposing that this process isn't just a random accident but the driving force behind a grand evolutionary cycle spanning the multiverse. This is the theory of cosmic natural selection, a fascinating and audacious proposal by physicist Lee Smolin. He suggests that universes don't just create other universes, they compete, they reproduce, and they evolve. In this view, the laws of physics in our universe aren't arbitrary or fine-tuned by chance. They might be the result of billions of years of cosmic Darwinism, optimized for one specific purpose: to make as many black holes as possible. To grasp this, let's start with the reproductive mechanism. Smolin's theory embraces the idea that a new universe can be born from the singularity inside a black hole. But he adds a critical twist. When this new universe is spawned, the fundamental constants and laws of physics might undergo a slight, random mutation. It's a cosmic form of genetic variation. The new baby universe won't have the exact same physical parameters as its parent. The strength of forces or the mass of electrons might be minutely different. Some of these new universes will be stillborn, their constants set in a way that prevents the formation of stars and galaxies altogether. Others might live but be barren, expanding into cold, empty voids. But a select few will have just the right conditions not only to form stars and galaxies but to produce something crucial: a prolific number of black holes. This is where natural selection takes over. A universe that is highly efficient at producing black holes is, by the rules of this theory, a universe that is highly effective at reproduction. Every black hole it creates is a potential portal to a new cosmic offspring. Therefore, universes that have physical laws conducive to black hole formation will have more children, passing on their favorable traits to the next cosmic generation. Over unimaginable eons and countless cycles, the multiverse would become dominated by universes whose laws are fine-tuned for one thing above all else: maximizing black hole production. Our own universe, with its specific balance of forces that allows for the life cycle of massive stars and their dramatic collapse into black holes, might not be a lucky accident. It could be a highly evolved product of this process, a universe that has won the cosmic reproductive lottery. This provides a stunning and testable answer to the puzzle of fine-tuning. Why is the cosmological constant so small, allowing galaxies to form? Because if it were too large, the universe would have ripped itself apart before any stars could form. Why is the carbon atom so perfectly structured to be created in stars? Because without carbon-based chemistry, life might not arise, and without intelligent life to eventually ponder such things, we wouldn't be here to ask the question. But more importantly for Smolin's theory, a universe without long-lived stars might not produce as many black holes. Every seemingly fine-tuned parameter could be seen as an adaptation for fostering an environment where black holes can flourish. We and all the stars and galaxies might simply be part of the cosmic reproductive machinery. In this view, hidden universes aren't just random variations. They represent different branches on a vast evolutionary tree, each with its own evolutionary history and physical laws optimized for their own version of cosmic survival and reproduction. Some might be ancient lineages that have perfected black hole production, while others could be evolutionary dead ends, universes that failed to replicate and are now fading into oblivion, their unique physical laws never to be passed on again. This perspective pushes us to consider that the very fabric of reality might be woven not from tiny strings or particles, but from something even more fundamental: information itself. This brings us to a theory that reimagines the multiverse not as a collection of physical places, but as a vast computational network processing every possible answer to every possible question. The quantum information multiverse suggests that the bizarre behavior of the quantum world is best understood not through the lens of physics, but through the principles of information theory, proposing that quantum states represent multiple parallel realities where different computations are running simultaneously, and that our singular experience of the world is a grand illusion crafted by process known as decoherence. To grasp this, we need to shift our thinking about what the universe is made of. In the digital age, we're familiar with the concept that complex things, a photograph, a song, an entire virtual world, can be reduced to a stream of bits, ones and zeros. The quantum information view takes this to the ultimate extreme. It proposes that at its most foundational level, reality is not made of matter or energy, but of information. The properties of a particle, its position, momentum, spin, are not inherent qualities, but rather represent bits of data. In this model, the universe is essentially a colossal quantum computer, and every interaction, from the fusion of atoms in a star to the firing of neurons in your brain, is a form of information processing. This is where the multiverse emerges with stunning clarity. In a standard classical computer, a bit can be either a 1 or a 0, but a quantum bit or qubit exists in a superposition of both states at once. It represents a 1 and a 0 simultaneously. Now, imagine performing a calculation with a series of qubits. A classical computer would have to try each possible combination one after the other. But a quantum computer, by virtue of superposition, can process all possible combinations at the same time. It's like forking a path into every conceivable direction in a single step. The quantum information multiverse theory posits that this isn't just a useful trick for computing. It is a literal description of reality. Every time a quantum event occurs, every calculation the universe performs, it doesn't choose one outcome. It computes all possible outcomes, and each result is realized in its own separate, parallel universe. These universes are not physical places in space, but distinct branches of a cosmic computation, each one a valid result of the universal equation. But if the universe is constantly computing every possibility, why do we only ever experience one definitive, concrete outcome? This is the final, crucial piece of the puzzle: decoherence. Think of the different parallel computations as different musical instruments, all playing their own tune in a soundproof room. From outside, you would hear nothing but a confusing cacophony. But the moment you open a door and listen, your act of listening, your interaction with the system forces you to hear just one instrument clearly. You become entangled with that one specific sound. Decoherence is that process of opening the door. It is the mechanism by which the countless parallel quantum computations become isolated from one another. When a quantum system interacts with its environment, when a photon bounces off an atom and hits your measuring device, the once coherent superposition of states rapidly leaks information into the surrounding world. This interaction effectively severs the connection between the parallel branches. Each branch continues to compute its own reality, but they can no longer interfere with or communicate with each other. From our perspective, trapped within one branch of this immense calculation, this process looks like the collapse of a probability wave into a single fact. We don't perceive the branching because our own consciousness, our memories, and our measuring instruments all become correlated with one specific computational outcome. We are like a character in a video game who believes their path is the only one that exists, completely unaware that the game has autosaved at every decision point, creating countless other timelines where different choices were made. The solid, classical world we experience is not the fundamental reality. It is an emergent property, a stable and consistent user interface generated by decoherence to allow conscious observers like us to navigate a tiny sliver of an infinitely complex multiverse of information. This theory doesn't just offer a multiverse, It provides a powerful and elegant mechanism for how and why such a multiverse would remain almost entirely hidden from us, revealing a cosmos that is less a place and more a boundless, ongoing computation of infinite possibility. But what if the grand cosmic story has no true beginning or end, but is instead an endless, rhythmic dance of death and rebirth? This brings us to a vision of eternity that is both ancient and modern, the bouncing universe theory. Picture the cosmos not as a one-off explosion from a single point, but as a celestial heart beating in an infinite cycle of expansion and contraction. Each heartbeat begins with a fiery Big Bang, unfolds into a period of flourishing growth, and then draws to a close as gravity pulls everything back together in a cataclysmic Big Crunch, which then becomes the seed for the next explosive beginning. In this model, our universe is not the first and will not be the last. It is merely the current iteration in an endless sequence of cosmic rebounds, each one leaving its own unique imprint on the fabric of reality. The elegance of this idea lies in its potential to solve one of cosmology's deepest puzzles, the problem of initial conditions. The standard Big Bang model points to a moment of infinite density and temperature, a singularity where the known laws of physics break down completely. It's a barrier that science cannot currently penetrate, leaving the question of what came before firmly in the realm of metaphysics. The bouncing universe offers a way out of this conundrum. There was no absolute beginning. Instead, the Big Bang was simply the latest turning point, the moment our universe transitioned from a previous phase of contraction into its current phase of expansion. Before that, there was another universe, and before that, another, stretching back forever in an infinite regress of cosmic cycles. This isn't just a philosophical notion, it's grounded in serious physics. To achieve a bounce, you need a mechanism that can overcome the seemingly irresistible pull of gravity during the Big Crunch and trigger a rebound. Some models propose that in the extreme conditions of the collapse, when matter and energy are compressed to an incredible density, new repulsive forces derived from quantum gravity come into play. Think of it like compressing a spring. At first, you can push it down easily, but at a certain point, the spring's internal energy fights back, pushing against your hand with increasing force until it finally snaps back outward. In the cosmic context, the universe itself could be that spring. The mind-boggling pressure of the collapse might activate a quantum repulsion, a force so powerful it can halt the inward rush of everything and reverse it into a new outward expansion, a new Big Bang. And here is where the theory gets truly fascinating, because each bounce may not produce a perfect replica of the universe that came before. The transition through the quantum-dominated crunch phase could act like a cosmic dice roll, introducing tiny, random variations in the fundamental constants of nature. Perhaps in the previous cycle, the strength of the electromagnetic force was a fraction of a percent weaker. Maybe the mass of the electron was slightly different. These minuscule changes during the rebound would reset the physical laws for the next cycle. Most of these new universes would be stillborn or barren, their constants set in a way that prevents the formation of atoms, stars, or any kind of complex structure. They would expand into cold, empty darkness or collapse again almost immediately. But through sheer statistical probability, given an infinite number of cycles, a universe like ours will eventually emerge, one where the numbers are just right for galaxies to form, stars to ignite, and life to evolve. We are not a miracle, we are an inevitability in an infinite sequence of cosmic trials. This provides a powerful alternative to the multiverse for explaining the apparent fine-tuning of our universe. Instead of an infinity of different universes existing now, we have an infinity of different universes existing in sequence. We just happen to find ourselves in one of the cycles that got the recipe right, a golden iteration in an endless chain of cosmic rebirths. This vision transforms our place in the cosmos from a singular, fleeting accident to a temporary chapter in an eternal story of destruction and renewal. Imagine for a moment that the universe is not a collection of particles and forces, but a vast, ongoing computation. This is the core idea of digital physics, a theory suggesting that at its most fundamental level, reality is not physical but informational. In this view, everything that happens from the orbit of a planet to the firing of a neuron is the result of a cosmic computer processing bits of information according to a set of underlying algorithms. Space and time aren't the stage on which the universe plays out. They are emergent properties, a kind of user interface generated by this deeper digital processing. If this is true, then the laws of physics we've spent centuries uncovering aren't fundamental laws of nature at all. They are simply the local operating system of our particular cosmic machine, the specific way our universe happens to run its code. This perspective opens a breathtaking new window into the multiverse. If our universe is a computation, then why should it be the only one? Different computational rules would inevitably generate different physical laws. Think of it like the difference between the various operating systems on our own computers: Windows, Mac OS, Linux. They can all perform similar functions, but they do so through different underlying architectures and command sets. A universe running on a different computational substrate could have a completely different set of fundamental constants. Perhaps in another digital reality, the speed of light is not a constant but a variable. Maybe gravity operates inversely, growing stronger with distance instead of weaker. In such a universe, the very concepts of space and time as we know them might not even exist, replaced by some other informational structure that allows for complexity and computation to occur. We can even speculate about the nature of the hardware running these cosmic simulations. Our universe seems to run on a substrate that allows for 3 spatial dimensions and a linear flow of time. But another digital universe might run on a system with a different number of fundamental variables, perhaps a 2-dimensional grid where complex patterns emerge to create the illusion of depth, or a system with multiple time dimensions, allowing causality to flow in more than one direction. The possibilities are as limitless as the imagination of a programmer. These hidden digital universes wouldn't be located in some faraway dimension. They would be running on entirely separate platforms, perhaps in a realm of pure information we cannot access, each one a self-contained simulation with its own unique rule set and history. This transforms the search for hidden universes from a quest through space into a search through the abstract landscape of all possible computations, a multiverse not of places but of programs. Now let's journey into the very fabric of what we consider to be empty space, because according to quantum field theory, the vacuum is not a true void but a seething, dynamic arena brimming with potential. This leads us to a theory that suggests the very ground state of existence isn't singular, but comes in a vast variety of flavors, each one capable of birthing a universe with its own unique set of physical laws. We are talking about the idea of quantum field theory vacua, which proposes that our entire cosmos might simply be one stable configuration in a vast landscape of possible vacuum states. To understand this, we need to reframe what we mean by nothing. In quantum field theory, every point in space is occupied by fields: the electron field, the quark field, the electromagnetic field. These fields are the true fundamental entities. Particles are merely localized vibrations in these fields, like temporary waves on a vast, invisible ocean. Even when we remove all particles, the fields remain, and they possess a lowest possible energy state. This is what physicists call the vacuum. But here's the crucial part: this lowest energy state is not always a simple, flat plane. For some fields, the vacuum can have a complex topography, much like a landscape with multiple valleys. Think of this like a marble resting at the bottom of a bowl. That marble is in its true vacuum state, its lowest, most stable energy configuration. but some fields are described by a potential energy landscape that looks more like a Mexican hat or a complex mountain range with multiple valleys. A marble could come to rest in any one of those valleys. Each valley represents a different vacuum state, a different stable configuration for the field. And the kicker is that these different vacuum states can have profoundly different properties. The laws of physics that emerge, the masses of particles, the strengths of forces, even the number of dimensions that become large and observable, are all determined by which valley, which vacuum state the field settles into. Our universe, then, is not the universe. It is simply a universe that happened to form in a region of the primordial cosmos where the various quantum fields settled into one particular set of vacuum states. The specific valley our Higgs field settled into, for instance, gave mass to particles, allowing atoms to form. But this was a random outcome. In other regions, the fields could have tunneled into different valleys, different vacuum states. Each of these other vacuum configurations would have given rise to a universe with completely different physics. One might have a much stronger electromagnetic force, making chemistry explosively violent. Another might have a vacuum energy so high that space-time rips itself apart instantly. A third might have a different symmetry structure that results in 5 fundamental forces instead of our 4. These other universes aren't far away in space. They could be domains that nucleated within the same primordial foam as our own, their different vacuum states creating an impenetrable boundary between our physics and theirs. We inhabit a single bubble of one specific vacuum, surrounded by a multiverse of other bubbles where the very rules of reality are unrecognizable. Now, let's shift our focus from the grand architecture of cosmic cycles and digital realities to a theory that operates at the most fundamental level of particle physics, yet opens a door to universes hidden within the very laws that govern our own. This is the world of supersymmetry, a concept so elegant that it has been called the next great revolution in our understanding of the universe, and one that naturally suggests a multiverse of a uniquely subtle kind. Supersymmetry, often abbreviated as SUSY, proposes a breathtakingly beautiful symmetry between the two fundamental classes of particles that make up everything we see, the fermions and the bosons. To appreciate this, imagine the subatomic world as a kind of cosmic society with two very different families. On one side, you have the fermions, the particles of matter. These are the quarks that make up protons and neutrons and the electrons that orbit atoms. They are the stubborn individualists. No two fermions can ever be in the same quantum state at the same time, which is why matter has structure and solidity. On the other side, you have the bosons, the particles that carry forces. The photon carrying electromagnetism, the gluon carrying the strong nuclear force, and the graviton hypothetically carrying gravity. These are the social butterflies, the communicators that love to congregate. They are responsible for transmitting the forces that allow fermions to interact and build the universe. Supersymmetry proposes a profound and hidden kinship between these two families. It suggests that for every known fermion, there should be a superpartner boson, and for every known boson, a superpartner fermion. The electron, a fermion, would have a partner called the selectron, a boson. The photon, a boson, would have a partner called the photino, a fermion. This pairing isn't just a whimsical idea. It emerges naturally from the complex mathematics of string theory and is considered by many physicists to be an essential missing piece of the standard model of particle physics. It would create a perfect, balanced symmetry at the highest energies, elegantly solving several major theoretical problems, such as the hierarchy problem, which questions why gravity is so weak compared to the other forces. But here is where the multiverse connection emerges with incredible force. If supersymmetry is a true property of nature, then it must have been a perfect symmetry at the moment of the Big Bang, when energies were unimaginably high. As the universe cooled and expanded, this perfect symmetry would have been broken, much like how liquid water can crystallize into ice in different ways as it freezes. The specific way this symmetry broke would have determined the properties of the superpartners and, by extension, the laws of physics in our universe. This is known as the supersymmetry breaking mechanism, and crucially, theorists have discovered there isn't just one way for it to happen. There are a vast number of possible ways for supersymmetry to break, each one resulting in a universe with a completely different spectrum of particle masses and force strength. This creates a landscape of possibilities not unlike the string theory landscape. Each possible vacuum state, each different way for supersymmetry to break, corresponds to a universe with its own unique low-energy physics. In one universe, the selectron might be incredibly light and detectable everywhere. In another, it could be so stupendously heavy that it played no role after the first instant of the Big Bang. This means the specific masses of the particles we observe and the specific strengths of the forces we measure are not fundamental laws dictated by a unique theory. They are simply the local bylaws of our cosmic neighborhood, the result of how supersymmetry broke in our particular patch of the multiverse. We inhabit a universe where the breaking happened in a way that allows for atoms, chemistry, and life. But an infinity of other universes exist where the breaking happened differently, resulting in realities that might be barren, chaotic, or governed by physics we can scarcely imagine. This suggests a multiverse that is not separated by vast distances in space or branes in higher dimensions, but by different configurations of the same fundamental fields that permeate all of reality. These parallel sectors, each with their own broken symmetry properties, could be thought of as overlapping layers of existence, forever out of phase with one another. The particles of our sector simply do not interact with the particles of another sector through any force we know of, because the symmetry breaking has given them entirely different properties and masses. They are ghost universes interpenetrating our own, made of a shadow matter that exerts gravity but is otherwise completely invisible and untouchable. This is a hidden multiverse of the most intimate kind, one where the alternate realities are not far away, but are woven into the very quantum fields that underlie our own existence, separated from us not by space but by symmetry. After exploring so many mechanisms for hidden realities, from branching quantum paths to cosmic collisions, we arrive at a theory that is less about how other universes might exist and more about why we can only ever observe one very specific kind. This is the anthropic principle, and when wedded to the idea of a multiverse, it transforms a profound mystery into what might be the ultimate selection effect. The mystery is this: why does our universe seem so perfectly, almost miraculously, fine-tuned for the existence of life? Change any one of a dozen fundamental constants by just a fraction of a percent, and the consequences are catastrophic. If the strong nuclear force was slightly weaker, hydrogen would be the only element in the universe, and no complex atoms could ever form. If the cosmological constant were a tiny bit larger, the universe would have expanded so rapidly that not even the first stars could have coalesced. It appears as if the universe knew we were coming, setting all its dials with exquisite precision to allow for galaxies, planets, and ultimately, conscious beings to ponder it. This apparent fine-tuning has led some to argue for a divine creator, a cosmic architect who designed the laws of physics specifically with us in mind. But the anthropic principle, particularly in its most powerful form when combined with a multiverse, offers a very different, and some would say more humbling, explanation. It posits that we should not be surprised to find ourselves in a universe that is hospitable to life, because we could not possibly find ourselves in one that is not. The principle is often stated as, we see the universe the way it is because if it were different, we would not be here to see it. It's the ultimate example of observational bias. Imagine a puddle waking up one morning and looking at the hole it occupies. The puddle might marvel at how perfectly the hole fits its shape, noting with awe how every bump and contour of the cavity exactly matches its own. This hole must have been designed specifically for me. The puddle exclaims, but of course the hole wasn't designed for the puddle. The puddle simply conformed itself to the shape of a pre-existing hole. In the same way, we conform to the universe we find ourselves in. We are not the intended result of its laws. We are simply the accidental byproducts of a particular set of conditions that allowed something like us to eventually evolve. Now, on its own, the anthropic principle can feel like a bit of a cop-out, a tautological statement that explains everything and nothing simultaneously. Its true explanatory power is unleashed only when it is combined with a multiverse framework. If our universe is the only one that has ever existed, then its improbable fine-tuning remains an incredible, inexplicable coincidence. But if there exists a vast multiverse, an infinite or near-infinite ensemble of universes, each with its own randomly selected set of physical constants and laws, then the mystery evaporates. In such a cosmos, every possible combination of physical parameters is realized somewhere. There are universes where gravity is so strong they collapse into black holes in a microsecond. There are universes where the nuclear forces are too weak to ever bind protons and neutrons together, leaving them forever barren. The overwhelming majority of these universes are sterile, dark, and lifeless. But in a sufficiently vast multiverse, every possible outcome, no matter how improbable, must occur. Somewhere, by pure random chance, the cosmic dice will roll a perfect sequence. A universe will appear where all the numbers just happen to line up correctly to allow for stars, planets, and life. We inevitably find ourselves in one of those extremely rare habitable universes. We are not a miracle, we are a statistical inevitability. The multiverse provides the lottery tickets, and the anthropic principle simply notes that we must be holding a winning one. This perspective doesn't diminish our existence, it recontextualizes it. We are not the central purpose of a finely tuned cosmos, but rather incredibly lucky winners in the ultimate game of cosmic chance. The hidden universes are not just a theoretical curiosity, they become a necessary part of the explanation for our own being. They are the countless losing tickets, the empty, silent voids where the constants of nature never align correctly. We cannot see them or interact with them, but their existence is what makes our own possible. They are the dark, silent background against which our single, shining, habitable world stands out. This idea completes a profound shift in our thinking, from a universe that seems designed for life to a life that is utterly adapted to the one universe among countless others that allows it to exist. And so we find ourselves at the end of this extraordinary journey, having ventured through 30 different windows into the vast and often bewildering landscape of cosmic possibility. From the bubbling foam of eternal inflation to the branching paths of quantum choice, from the holographic projections on a distant boundary to the shadowy mirror realms of antimatter and reversed time, a single, humbling theme emerges with startling clarity. Our universe, for all its immensity and splendor, might be just one small piece of a reality so grand and multifaceted that it dwarfs our ability to fully comprehend it. What's truly remarkable is how many different keys, scientific, philosophical, and mathematical, seem to unlock doors to this same breathtaking conclusion. Quantum mechanics suggests that every possibility is realized in a branching tree of alternate histories. String theory and its landscape point to a nearly infinite catalog of universes, each with its own unique physical laws. Thought experiments in philosophy challenge the very notion that our reality is the only one that could be considered real. These aren't competing ideas so much as they are different paths up the same mountain, each offering a unique vantage point on the same staggering vista of a multiverse. They collectively challenge the deepest assumptions we hold about our place in the cosmos, transforming the universe from a singular, lonely expanse into what might be a single page in an infinite library of existence. This isn't just an academic exercise, it's a profound expansion of human perspective. For centuries, we looked at the stars and wondered if we were alone. Now we look at the very laws of physics and wonder if our entire reality is alone. The possibility of hidden universes redefines the nature of mystery itself. The greatest puzzles of our time, why the constants of nature are so perfectly tuned for life, what happened before the Big Bang, the true nature of consciousness, may not find their answers within the confines of our own cosmic horizon. The solutions might lie out there in the physics of another universe entirely, forever beyond our direct observation, but not beyond the reach of our reason and our imagination. This leaves us not with a final answer, but with a thrilling and open-ended question. It makes the cosmos a place of endless wonder, a puzzle that may never be fully solved but will constantly reward our curiosity. So we want to turn it over to you now. Which of these 30 theories reshaped your understanding of reality the most? Was it the elegant clockwork of eternal inflation, the mind-bending implications of the quantum multiverse, or the philosophical grandeur of modal realism? Dive into the comments below and share which idea you find most compelling. Let's continue this conversation, because the search for understanding is a journey we take together, always looking for the next hidden door in the fabric of